Hello, everyone. Welcome. A few announcements before we get started. First off, I'd like to thank our sponsors, particularly our Inner Circle sponsors, Critical Stack and Velomail, as well as some of our stellar sponsors, Amazon, BlackBerry, and Cylance. We have a huge amount of sponsors this year, and we really could not do this conference without them. They're part of what makes this possible. So please go out there, see some sponsors, thank them. Please silence your cell phones. At the end, if there are questions, I will be walking around with a microphone. Make sure to speak your question into that microphone so the people at home can hear you. And that's all the announcements I have. So without further ado, here are Ben Sawyer and Matt Canham.
Hi, thank you very much. Before we start, I just want to say that whatever we say today is not the opinion or position of the U.S. Army, so don't hold them responsible.
Excellent. Hi, I am Dr. Ben Sawyer. This is Dr. Matt Canham. We're with the Laboratory for Autonomy Brain Exchange at the University of Central Florida. And today we'd like to have you look at a problem that we've been looking at for some time. And we're here actually to enlist the opinion and the help of this community in continuing and identifying the direction of our research. Today we'll be talking about Infosec as it relates to brain-machine interface and the very near future, and in fact the present. So LabX, or the Laboratory for Autonomy Brain Exchange, is a group that really looks to engineer systems that optimize data flow between humans and machines. Basically get away from the slowest possible thing, which is poking a screen with this chunk of meat, and get anything faster or better. We do that through neuroengineering. So neuroengineering basically means hooking up computers to the brain or to pieces that touch the brain and using that to move things faster than fingers can. Neuroergonomics, which means watching people as they use tools and understanding their brain state as a way of re-engineering and redesigning, for example, interface. And neuromodulation, which is the act of projecting into the brain in order to change your state. In much the same way you do with caffeine. Does anyone here use caffeine? Then you're very, very comfortable with neuromodulation. It's just that a Red Bull is much slower than electric current. And it would be nice to be able to have that jolt in the moment, and other things like that jolt. I'd like to just point out today that if you're interested in talking to us, our email, which will show up at the end again, is labx@ucf.edu. So without further ado, Matt, tell them a little bit about what we're doing.
All right. So I would like to point out that we actually submitted this paper several months before Elon Musk made his Neuralink announcement. However, the timing of that was very good for us. And so Elon, if you happen to be watching this, please send us a message. We'd love to chat with you. But the reason I want to bring this up is that I think that it shows how quickly we are moving towards consumer devices. In that announcement, Mr. Musk mentioned that they want to begin human trials within 1 year, so 2020 is the target date to begin human trials, and they want a consumer device within 10 years. So we'll see if that happens, but we have some very large companies such as Neuralink, Facebook, and others that are actively working to try to bring this onto the market. So just a quick overview on how the nervous system works. At the very base level, we have neurons, which are cells that communicate with one another. And the way that they communicate is that they get these upstream signals. Sorry, let me use the laser. They get upstream signals from dendrites, which are connected to other neurons that are sending these signals to the neuron. And after a certain threshold is met or exceeded, then the cell body, which is the soma or the nucleus of that neuron, will then decide to fire. And when it fires, it sends an electrical impulse down this thing called the axon, which sends this electrical impulse down that axon to the synapse, and that releases neurotransmitters across what are called the synaptic gap. Downstream from the synaptic gap is another dendrite, which is connected to another neuron, and so on and so forth. And so that's how these messages get passed. The importance of this is something called the action potential, which is what happens when this electrical current travels down that axon. And the reason that that's important is that's something that we can detect, and we're going to talk about that more in just a minute. Just a very quick high-level overview of some of the anatomy of the brain. You can see different components here, but the three that I really want to focus on are the cortex, which I'll talk more about in a second, but the amygdala, which is this sort of almond-shaped, orange-reddish sort of thing here in the middle. The amygdala is responsible for emotional processing or making sort of these emotional or affective associations to stimuli. And the reason that this is important to what we're talking about today is that these associations can happen at a non-conscious or an unconscious level. And this is actually what protects us a lot from danger. This may play a very significant role in things like PTSD. So there was a case study of someone who witnessed the 9/11 attacks and didn't really have any real symptoms or anything, but then a full year went by since those attacks, and suddenly, just completely, literally out of the blue, was a clear blue day, fall, and the air was very cool and crisp in a very similar way to the day that that 9/11 attack happened. And all of a sudden, this gentleman just was overwhelmed with a panic attack. It didn't really understand why. And one of the main reasons that may have been occurring was that the amygdala had made this association between those weather conditions and danger, but he himself had no idea that his brain had made this association. So this demonstrates how the brain can make associations between things that we have absolutely no conscious idea or understanding that it's making. In contrast to that, we have the hippocampus, which is this thing right behind the amygdala, and that's responsible for the consolidation of memory. And so this is what transfers basically short-term memory into long-term memory. This happens a lot during sleep, and so you can actually suffer from something called sleep-induced amnesia, where if you stay up for several days in a row, you will actually lose very significant chunks of time. And one of the reasons for that is that your hippocampus is not consolidating those memories. Also in brain trauma, we see sometimes when people receive brain trauma, so they'll get a concussion or something like that. If there's damage to that hippocampus, there's a very low probability that that person will have any sort of memory for that event. Instead, they'll just have this chunk of time that's lost where they were doing something and then the next thing they knew, they woke up somewhere like in a hospital. Okay, so then coming back to the cortex, when we look at the cortex, this crinkly sort of outer sheath of the brain that we typically think of when we think about the brain, the cortex is divided roughly into 4 regions. And in this case, this pink area on the left-hand side would be the front, and that is the frontal lobe. And right behind that, we've got the parietal lobe, which kind of sits up on top, and then the temporal lobe, which is kind of right by the ear, and then the occipital lobe. The frontal lobe is responsible for what we call executive functions, and these are things like attention, working memory, decision-making, reasoning, and coincidentally, when someone's very upset, it tends to drive the attentional focus towards whatever's upsetting us, but that also distracts us from things like being able to reason clearly. So if somebody's very emotionally upset, their chances of them being able to reason through something very well is probably not so good. Likewise, fine motor control, I should specify, it's not just motor control, but it's fine motor control, is controlled by the premotor cortex, which is just kind of in the back end of this frontal lobe here. if you talk to any veterans, one of the first things that goes out the window in combat when things are really intense is this ability to do fine motor functions. Your gross motor skills will still be there, but your fine motor skills aren't so good, and that's one of the reasons. In the parietal lobe, we have somatosensory, which is your sense for your body. So when you experience touching sensations, like on your hands or on your cheek or anywhere on your body, there is a corresponding representation of that part of your body in your somatosensory cortex, which is right here in the front of the parietal lobe. Temporal lobe is also known as auditory cortex. This is what processes auditory information. It's also primarily responsible for long-term memory. And then finally in the back we have the occipital lobe, which is also known as a visual cortex, and this is what processes visual information. Now, these don't operate in isolation, okay? So if you see something, that information goes from your eyes over here back through the optical nerve to the occipital lobe in the visual cortex, but then very quickly it moves forward to these other lobes. So if you see a baseball coming at you, that information is initially processed in your visual cortex, but your temporal lobe starts processing that in trying to recognize what that object is and recognizes it as a baseball, while your parietal lobe is calculating the trajectory of it coming towards you and trying to understand where that baseball is spatially in relation to yourself.
So, looking at this, here, come back one.
Oh, sure.
Looking at this, have you ever tried to explain how a modern computer works to someone who's naive? It's a strange moment, right? There's all of these layers and all these miracles happening, and you're like, no, listen, hardware and software, and to them, it's a screen and it's a tool. I'd like you to take just a second and think about your own brain. You don't do that very often. How many people here have held a brain in your hands? I don't care what type of brain. Okay. It's a fascinating thing, right? It's a lot smaller than the head. It's padded by a lot of things. Your own brain is likely think a large grapefruit. So just think about that for a moment. It's sitting there between your ears right now. It's the reason that you're looking at me and talking to me. That object is, in fact, an amalgam of many different pieces. And a change to any one of those pieces can have huge effects on what you can do and who you are. And we've all read stories about that. Some of us have people in our families who have those issues. People who have issues with memory. It's very interesting to look at a person, and very frightening, and see how, although the whole is still them, pieces can change. And in fact, if you'll go forward a slide, this is something we write about a lot. And science fiction has been pulling on this thread our whole lives. And in fact, one of the strange things about what we're going to talk to you about today is even deep experts in this field have trouble separating the science fiction and the poetry and the lore that we've been exposed to our whole lives from the reality that is changing every single day. So what I'd like you to do for a second is just think about where you get your ideas. The Ghost in the Shell is entirely about hacking brains. The Gibson Neuromancer books are deep in everybody's understanding in this community of what brains are and how they react with technology and what that means. Right now, Ian Banks' books, Look to Windward, are really what Musk talks about when he talks about Neuralink. The neural lace there is what his link to this world is. And so one of the fascinating things that comes out of this is it gets a little hard to separate sometimes the narrative, because the scientists are using the science fiction to inform the reality. And so think about that as we talk about what's actually possible right now. Because what we're going to do now is get away from how this lump of jelly between your ears, if you've ever dissected a brain, it's like dissecting a cup of yogurt. It just reveals nothing. But how we can get into it and start to understand what's coming out of it, and then how we can manipulate that. So talk a little bit about sort of the constituent pieces here.
And so if we're reading from the brain, there's really two types of signal that we can detect. One is blood flow. And so the neurons I talked about earlier, they're just like muscle cells, really. You know, when they're working, they're consuming oxygen, right? So they need that replenishment of oxygenated hemoglobin. And so what we can do is we can actually detect when that starts to differentiate and where in the brain that differentiation is happening. And so that creates something called a bold signal that we can then detect. And you can see examples of that on the left. Likewise, when those neurons are firing, they're producing these electrical currents, and that's also detectable by an EEG like what I'm wearing right now.
So consider how you would determine what a computer is doing by watching its thermal signatures, or by watching how much energy it uses in any given place. You might not be able to tell much, but you might be able to tell that when it's doing visually complex geometry, certain parts heat up, and those are related to that. It's an association game when you start using this. In fact, what you're looking at here on the bottom is a great study. On the left are people being tickled and laughing. And in the center are people being tickled and trying to inhibit their laughter. Stop. And on the right are people voluntarily laughing at funny images. And you can immediately look at the areas where the most blood is used and start to draw associations, right? You can say, oh, well, the difference between tickling and laughter and tickling and inhibition might be the things you use to inhibit things, right? So this is the sort of thing that scientists use to tease this apart. Electrical signals are a little different, and a great metaphor that's used in neuroscience is imagine sitting on the outside of the Astrodome with a stethoscope listening to a game. What could you tell? You could probably tell when teams score, right? You could tell maybe if the audience is seated in teams, who scored, right? By who cheers. There would be moments that you heard over and over again. We all know the sound of a soccer score, right? You can hear it in your head right now. It's your brain. So these electrical signals are also quite useful. And in fact, we are teasing them apart right now in ways that would have been science fiction only 5 years ago, 10 years ago. And in fact, it's interesting to note, if you look at MindFlex there in the middle, MindFlex is a game that's been in production for almost a decade that lets you levitate balls using your mind, using EEG. It's a very, very simple implementation of EEG. What is possible now is an order of magnitude more nuanced, and that has a lot of interesting implications. I should also note that these things are used in combination. We'll talk more about that in just a moment. So it's not all about output. We can input to the brain as well. I mean, I'm doing it right now. I'm inputting to all your brains. It's fairly simple, but what we can do is actually project force directly into the brain. So transcranial magnetic stimulation has been around now for some 60 years, 80 depending on how you talk about it. And it is the use of magnetic fields, very focused magnetic fields, to change how neurons fire. And very good at doing things like increasing excitement or decreasing excitement in parts of the brain. Transcranial direct current stimulation is one of my favorites. There's a homebrew community of people attaching sponges to their heads and running current through. Are there any of you here? Awesome. I've built one too. These are people actively running current through their heads, and their technology is a direct descendant of electroshock therapy that you've seen in One Flew Over the Cuckoo's Nest, refined by decades and decades and decades, and something that is enjoying a kind of a renaissance. What you're seeing on the bottom there is a very high density array that can stimulate areas of the brain with more resolution than we've ever been able to before. Deep brain stimulation is a fascinating thing in which you stimulate from the inside of the brain out. It has been used to treat a number of neurological diseases, but interestingly, recently you'll find it being piloted for things like losing weight. It's a brave new world, you know. Finally, these sensory and prosthetic implants that give input to the brain are a really interesting thing. Who here has a friend or a relative with a cochlear implant? So these are fascinating things, and they're usually implanted as young as you can. And the reason is the younger you get this into someone's head, the better their brain adapts to it, and the better they'll be able to hear. So these really are implants for children, as the picture shows. There is a similar implant, which is becoming more and more common, which does the same thing with the retina. It's very much the same idea. Feeds information directly into your optic nerves. Last but not least, in this memory piece by Lawrence Livermore Labs, which they showed off in 2014, tickles your hippocampus when you should be remembering things and boosts your ability to do so significantly. So it's not just about sensory. We're looking at futures where you might be able to change many functions of the brain, augment, and we should talk a little bit later, disrupt. So input, output, but the really interesting thing that's happening right now, if you go to the next slide, is input-output systems. Because we're at the point where input and output are good enough that we can start building systems that do it in a cycle. And this is what LabX does, and this is what I'm most excited about. These are fascinating technologies. Look any one of them up for hours of weird reading. Transcranial Doppler is Doppler radar, refined to reach in and measure blood flow in exact locations in the brain, and also capable of stimulation. Optogenetics changed the genetic code of cells to make them emit light or receive light to make them fire or when they fire. And as a result, you can create a light interface to the brain, not to my knowledge being done with humans, absolutely being done with mice. These ECOG DICES systems are fascinating, and these are what Neuralink is promising. So Neuralink's technology is joined by another group called Cortex, who are laying electrodes across the surface of the brain and stimulating regions that they touch. Another very interesting group at Brown is sprinkling what it calls grains across the surface of the brain, each one of which can be reached via a specific electromagnetic spectrum and reflected back. So these actually sit as tiny little pieces in your brain and can be written to and read from. A very interesting future there. And then we've got the unknowns. Top right, you're looking at a rather cryptic picture that Deep Water put out. Deep Water grows out of Facebook. They are focusing light inside the body. And they're doing that to create high-resolution imaging and do things like take your MRI out of the hospital and put it in an ambulance. But they're also creating brain-computer interface, which may or may not read and write. I believe the general consensus in my community is it does both, but nobody knows. Facebook just published in Nature a week and a half ago. When individuals are answering questions, Facebook can pull that out of their heads with an accuracy of about 70%. That's without using the audio. They're pulling that directly out of their heads. This joins a lot of very similar, very invasive findings, you should say. And so I want you to just consider this chunk of jelly between your ears for a second more. It's been yours your whole life. Really, whatever you're thinking right now, it's yours. And this is near the last moment that that will be true going forward. For some people, it's already not true. And the opportunities are amazing. And the possibilities for abuse are equally amazing. And that is why we are here to talk to you today. So I just want to take a moment and then pull you into the present. This is Jiang et al. From 2018. You're looking at two individuals who are both looking at a Tetris screen. You see them top and bottom? The senders, sender 1 and sender 2.
Did you all manage to find a brain yet?
We did not. Did you bring us a brain?
I didn't want to touch it without gloves, so we got the tag's still on it. But
This was a request that I made. I said I would like a brain and also I would like a pony. Tragically, the human brain was a little hard to bring with us. It turned, You are my hero. You have absolutely made it. Hello, fella. I grew up with horses. This makes me very happy. Here, we will name one of them Charlie. Thank you. Perfect. So, wonderful. You've got two people watching Tetris, like just watching the shapes fall. We've all done this. You ever watched your friend play Tetris? Monitoring their watching Tetris, that information is pulled out of their brain through a brain-computer interface and moved to another computer where it is set up with a receiver who's on a bidirectional link. And that person can't see the Tetris screen, but they can play it because they're receiving the information from the two senders. I just want you to think about that for a second. This is where we are right now. And by the way, because of academic research, this was done in 2016. We're in way more interesting places right now. But your understanding of where this technology is, like most people, is probably a little out of date. Like a lot of things, it's moving very quickly right now. And so things that were science fiction are quite suddenly reality. So what we're going to do real quickly is set up Matt on a live connection. So give me just a moment here. I see. So Matt is wearing an EEG headset, and what we're going to do is give you all an opportunity to watch what's going on in his head, live, right now. This is actually how easy it is to connect. This thing would have been a miracle 20 years ago. I'm delighted that I'm doing research in a time when this isn't the size of a refrigerator. What you are looking at is raw output from 3 electrodes on his head. You're listening to the electrical signals, essentially, from his brain. And these are the types of signals that could be used to understand a variety of interesting things. And to talk to you about what that means, I'd like to show you some examples of brainwave activity so you can start to understand how somebody might use this as an exploit. So here we are looking at Matt's electrical neural activity. And to be clearer here, what we're looking at in the top is this ongoing pattern that you see here. And this pattern is the sum of all of these neurons firing over time. And in fact, you can see patterns in it. So if you look up at the top, here's what somebody who is excited or relaxed, drowsy, asleep, deep sleep, coma looks like. Matt's a little closer to the excited side of the spectrum right now. The interesting thing is, like any signal, you can clip little pieces of it out. Remember the soccer goals? There are moments that mean things, and we're learning them. That they're a vocabulary of the brain in the way that there's a vocabulary of a soccer game, right? And so those moments, those ERPs, can be pulled out and they can be used for things. So remember we talked about informing AI by listening to the brain. If you make an error, I can pull that out of your head by listening to this signal, maybe as much as a second faster than it would take you to, say, step on the brake with your foot or press a button with your finger. That's a lot of time in some contexts, I think you'll agree. So there's this running joke of why is there not an undo button on a jet? By the time you press the button, you're dead. But if you could move that in 50 milliseconds, maybe you wouldn't be dead. The interesting thing about pulling out these ERPs and using them in systems is you can imagine that the machine learning, the analyses that are used to pull these out are also indicative of the ability to play them back, to modify, and also if you start thinking about it in a penetration standpoint, they look a whole lot like a lot of situations where you might interact with a server. Denial of service is a possibility, right? Spoofing, absolute possibility. Could you get the machine to think the human had done something they had not? Unquestionably. Could you get the machine to not know that the human had done something they had? Absolutely. And so this is where we get into an interesting set of questions that are really the heart of our talk. And thank you for being patient as we give you the pieces to get here. The world is becoming a very interesting place, but the same skills that all of you employ every day can be used to change it. Hold on, I'm going to pull us down a slide here. So what I'd like you to consider for a second is just a few ideas. When you connect machines to the brain, encryption is rare. Why? Well, first, latency is really undesirable, right? How many people would like an artificial limb that works on a 1 second delay? Doesn't this just sound like the worst? And by the way, many of them work on a delay. We're working on that. Power is precious. Every second that your extension of ability continues is precious to you. How do you feel when you lose your smartphone? When that's taken away from you? People don't want to give up power to things like encryption. Also, implanted systems are long lifespan. I mean, everybody talks about long lifespan systems, but by definition, something that's put under your skin is supposed to exist for your whole life. You don't want to cut it out again. And as a result, these systems are very open, very unrestricted, and the medical community rationally keeps them that way, although maybe they won't for long. Ethics really restricts scientific research. I have to work very hard with panels to do human subjects research, but hackers won't, not some of them. For the same reasons that it's hard to do phishing research, because it's hard to ethically send 1 million emails before you have your morning coffee, but spammers can do A/B testing in giant numbers. For the same reasons, we're going to learn some things from the people who compromise these systems in large numbers. Also, the brain has a lot of side channels. If you've got an insulin pump, I can stop your brain, right? So when you talk about side channel attacks, realize that your entire body, your entire peripheral nervous system is a side channel to your brain. So really, I'd like you to consider the fact that humans have become cyberphysical systems, and we need to start treating them as such.
So this is, let me just skip ahead for just a second. So what we're seeing is really a migration from traditional cyber, where this information is in the cloud, to the interface, to the brain itself. And we'll come back to this, but I just wanted to show this for a second while we discuss different possibilities for attack here. Now, on the more traditional side, and let me say real quick also that one of the goals that Ben and myself have is to develop some sort of security framework for neurosecurity. And I realize that the 3 pillars of information security are not perfect. They have their flaws, they're limited, so on and so forth. But as a place to just describe kind of the beginnings of this and to have this initial conversation, we've got confidentiality, integrity, and availability. Confidentiality being the protection of protected information or private information, integrity being the protection of that information from being modified without authorized consent, and availability, having access to that information. So if we look at from the transmission of this information, say from one brain to another, one brain to the cloud, or some sort of system like that, what have we seen so far? Well, transmission, interception of the transmissions. Well, this has been done. There's been a group that has already looked at unencrypted signals and have been able to reverse engineer that to the point of even reversing PIN numbers. I don't believe that they've done passwords yet, but that's kind of the next stage. Altering the integrity of that information. So in this particular case, the researchers were looking at a brain-controlled remote control car. And this car would turn left if you thought, left, and turn right if you thought right. And they reversed that so it would do the opposite of what you were thinking. Ben mentioned earlier the neural control of a prosthetic device. Well, you can imagine very quickly that if you did something very similar to that attack to the remote control car, but to your prosthetic arm, it could have very detrimental effects. And then availability, simple denial of service. That's something that is very easy to do at this point from the technology perspective. However, when we move downstream a little bit, we start talking about the actual interface between the machine and the brain, now it starts to become interesting. So again, reversing pins. The reversing of the pin was happening purely from that ERP signal. The researchers were just showing numbers to the subjects, and as the pin was being revealed, they would show an amplified P300 wave, and from that they could decipher what their pins, their security pins were. Direct neural stimulation. I mentioned the mapping of the cortex. Well, the way that that functional specialization was discovered in the first place was in the 1950s. Neuroscientists and neurosurgeons at Walter Reed Medical Center were actually doing open brain surgery without the skull. And in the process of doing this, they would stimulate different parts of the brain. And as they would do this, people would spontaneously start laughing. They might experience smells or tastes. A few reported hearing voices or music. And this is all that's happening here is that somebody is placing an electrical probe into the cortex, a certain part of cortex, and then stimulating that. So you can imagine that if that's possible, if somebody has an embedded device and someone is able to access that device in an unauthorized way, well, then you've got a really interesting avenue of attack there. Consciousness attacks, apparently there's actually a consciousness switch in the brain that can be tripped through stimulation. And this would be an example of denial of service, obviously. And again, through the same technology as what we saw from the Walter Reed studies. Okay, so that stuff's interesting, but let's get into the really weird stuff, right? So let's see where we can really take this. So confidentiality, direct neural stimulation, we talked about reading from the brain, right? So reading blood flow, reading electrical activity. The question is how far away can this happen? You know, how far away can you project an infrared laser and actually read the activity that's happening in someone's brain? That's an open question right now. How far away can you read electrical activity? It's possible to read an EKG signal from 200 meters away from one person. So how far away are we from that being applied to the brain and being able to receive signals that we can then decipher? Operant conditioning. So B.F. Skinner developed operant conditioning in the early part of the 20th century, from probably about the 1920s till about the 1950s. In psychology, this is one of the strongest theoretical principles in all of psychology. Operant conditioning works. B.F. Skinner trained rats to do a whole host of activities by giving them positive rewards or by giving them punishers. And by altering the sequence of these in the learning cycle, that he was able to teach them how to do very, very intricate tasks. And afterwards, he applied the same principles to his children, and, well, apparently they worked there too.
They turned out fine. Turned out fine.
Nothing to see here. He wrote a book about it too, I think, actually. Yeah.
It's a great book.
If you've ever seen the movie Clockwork Orange, this is the principles that they were using there to reform the criminal. Okay, so let's take that one step further, right? We already talked about how we can stimulate parts of the brain. So what if we could stimulate pleasure centers? Or what if we could stimulate pain? And what if we couple this with something like geofencing? What if we don't want you going to work? So we give you a dose of pain every time you enter a geofenced area. Or what if we just make you feel nauseous? If you kind of let your imagination kind of run wild with this for a second, you can really see how you could actually very intricately shape someone's behavior. This is old technology, but in 2009, the Army developed a remote-controlled beetle, flying beetle, and this had a chip, and it was very similar sort of system where different parts were stimulated and they would fly in different directions depending on where the operators wanted that beetle to go. In principle, there's no reason that we know of that this couldn't also be applied to human beings. And then finally, we want to talk about directed energy. So things that are in existence right now. Has anyone heard of the mosquito? Okay, a few. This is a very interesting device. So this, it emits sound, but it's sound at a frequency that you cannot hear any longer after you're about the age of about 25 years old. So, if we want to do a denial of service attack against teenagers because we own a convenience store and we don't want them hanging out after 10 a.m. or 10 p.m. outside the door, well, we can turn on this emitter that projects this sound that they cannot stand because it sounds like this very high-pitched, whiny mosquito in their ears. But if you're over the age of 25, you don't even know that it's happening. Somebody else used the same technology, but uses it as an auditory alert on the text message apps. So now the adults can't hear when the kids are getting a text message. In 2009, there was an epilepsy website that was hacked. And in this case, the actors actually caused the website to project a light of a certain intensity at a certain frequency as to induce seizures. And these are in people who are going to this site for help. And we're going to talk about Cuba a little bit more in just a second. Yeah, but that's another interesting case study.
So when you talk about the neurosecurity spectrum, and we really think there is a spectrum here, you're really moving from the traditional to the exotic. And I'd like to talk about the traditional, what we're all very comfortable with to start. Information infrastructure attacks work beautifully here, right? If you have an individual who has a capability through an implant or through even a system that's exterior, taking that capability from them gives you great control over them, especially if it's an insulin pump. I want to be clear. So these traditional types of attacks are absolutely capable of affecting the brain in a side channel or even direct, in some cases, situations way. BCI, brain-computer interface, brain-machine interface attacks, take this another step. And I want to be clear about what that means. When a system touches your peripheral nervous system or your central nervous system, or touches some part of your body that gives you access to those systems, getting more and more sort of side channel. I don't know if I like that term, but it's the nicest term we could find for these ideas. It gives you the ability to project force, and it may also give you the ability to read. So, you may think as you looked over the attacks that Matt was talking about, but I've never heard of anything like this. The reason you haven't is that the ethics of testing these types of things are really very complicated. And specifically, even the mosquito. So here's a seemingly innocuous situation is working its way through the courts because cities have put it in public parks where it does exactly what they intended to. But I think, is anyone in here under the age of 25? I have to be careful what I say. I joke. But I think you will all agree that this has some really strange ethical implications. You are adults. You are participating in the same society that we are. Isn't it a little strange that we could hang something up that makes you uncomfortable in an area? That seems like potentially an evil technology from a certain point of view. And there are other people in this room who've made a note to purchase it. So the point I'm making here is that these BCI, BMI attacks get really very complicated very quickly in terms of ethics. But if you're not using ethics, you'll be able to test a lot of things quickly. And I think that's what we're going to see. In fact, it's what we're going to ask you to do as thought experiments, please, in a few minutes here. Neural attacks get even a little stranger. In the same way, I saw a talk on satellites today, that you can use direct projection of force, DEWs they call it, direct energy weapons on a satellite. That's very much a cyber attack if you're hitting a satellite with microwaves and cooking its processors or just disrupting them for a period of time. Neural attacks run the gambit from using channels like BCM, BMI to long range or even short range neuroimaging attacks to the fact that you might really be able to project force directly into people's heads. And the type of understanding that the scientific community is building right now can absolutely be used to accomplish these sorts of things. And so when we look at the traditional to the exotic, I think we can also understand that the exotic is actually a fairly near future and may actually indeed be a present. So with that, I think, Matt, let's talk about attack surfaces and vectors in this space. In a very traditional sense, something that's been around for years. There are over 2 million people who have cochlear implants right now within the United States alone. And more as it goes along. It's a very well understood type of implant. So in a traditional cyber sense, the interesting thing is that these are now cell phone connected. iOS is the largest server of implants for data anywhere. And what you can do is you can listen to podcasts, you can answer your phone through your implant, anything you could do through a Bluetooth headset. So there's a lot of very traditional attacks. I mean, you could just take away a person's ability to have that service and harm their life. Take it another step. If you step away from the phone, suddenly you're in a small proprietary cyberphysical system. Standard things in weird little cyberphysical systems apply. You might not be on IP, you might be on some weird other protocol. These things have been constructed since the 80s. But it looks very similar to cyberphysical systems until you start tickling the aural nerve. And I have to say, this is peripheral nervous system, this is sensory nervous system. But certainly playing loud, repetitive noises to people is a technique that has been used in interrogation and torture for some time now. And is now directly available to you through being able to reach out and through the fact that it only takes a tiny amount of electrical current relative to modern electronics to project a lot of force into the brain, right? So let's take another step though. Just with a cochlear implant, could we do the thing we were talking about earlier where you condition people? What if every time you stepped into an area, there was a sound that was truly unpleasant in your ears? You'd stop stepping into that area. So with that, I'd like to take another step and have Matt tell you about a real exotic.
So I mentioned Cuba earlier, and some of you may have heard of this, some of you may not. But between 2016 and 2018, there were multiple employees at the US Embassy and I believe also at the Canadian Embassy in Cuba who experienced very sudden onset of this very loud, high-pitched, like a chirping or a screeching sort of noise, and very shortly after experienced dizziness, trouble seeing, sometimes pain, and also sometimes the ability to function with their motor functions. And this has been fairly controversial because at first the people weren't believed, but they all had very similar accounts of what had happened. They had either walked into a particular part of the embassy and then just like somebody flipping a switch, all of a sudden this thing happened to them. And a few reported collapsing. Others reported being in a place and then all of a sudden something just came on and they heard this screeching noise. So as I mentioned, there's been a lot of skepticism about this. So just 2 weeks ago,
July into August.
Well, yeah, it was the July issue of JAMA, the Journal of American Medical Association, released a study that was conducted by the University of Pennsylvania, where they actually did MRIs on these people that were reporting this. And they compared them to two control groups. One was sort of normal, statistically normal sample, population sample. The other control group was traumatic brain injury, TBI patients. And what they found was two things that were very interesting. One was that these employees who were reporting this reported a severe, or excuse me, their MRIs revealed a severe degradation and reduction of white matter in their brain. And this was generally, but it was also in certain cases localized. And remember, I mentioned that these people reported trouble hearing and trouble seeing. Well, two of the localized areas were an auditory and visual cortex. And in those localized areas, they showed reduction in white matter and in gray matter. White matter, you can probably speak to it in a second, but it's not very well understood in terms of what its function is, but essentially what it does is it helps to relay communications between different parts of the brain, basically. And it's made up of primarily myelin, which acts as an insulator for those neurons that are passing on messages.
You need it very, very badly.
Not good if it's degraded.
So I think the interesting thing here is that this, in my mind, doesn't sound like a sonic weapon. It sounds like something that as a side effect is causing the sound. And in fact, this guy Seth Horowitz, a neuroscientist at Brown, had very similar thoughts on this. It's an interesting moment. We're going to keep watching it. But I think in light of what we talked about, you can see that this exotic future may be closer than we imagine. On that note, really, if you think attack, detection, defense, there's a really interesting set of questions here. What do we do? So how do you detect these things? Baselining is something that at a certain point in history was done very infrequently on computer systems. Now anyone who cares about their computer systems builds a baseline and understands the difference. That's also, by the way, done by football teams to understand concussion damage. Maybe we need to start doing it on all of us to understand what we used to be like. It says the US, the State Department would like you to move to a location where the sound is not present, in the grand tradition of get under your desks and cover your head. Prosthesis, cyberphysical systems. I mean, there's already malware scans. Maybe we could build more hardened systems, but boy, they sure cost power and latency. What are we doing here? We don't know. Open question. Conditioning, boy. You know, how do you give a cognitive baseline to somebody who might not be willing to give you one, right? Conditioning can do really powerful things to people. For a little bit of history of that, look at the entire history of war criminals. So this is a really interesting set of questions. And really, we'd like you guys to give us some thoughts and talk to us at Neurosecurity on Twitter, or if you prefer, there's other ways to reach out. What you're watching here is a rat that has a single wire connected to the pleasure center of its brain. And it's pressing a pedal that gives it a very small pump of current. And every time it does, it experiences pleasure, pure pleasure. It doesn't want cocaine if you give it to it. It's that good. It doesn't have sex. It usually, in this case, will die of dehydration because the pedal is better than taking a drink. It's fascinating to take a moment and think about this lump of jelly between your ears and how much it's you, but also how much it is a set of triggers for you. You know, you say pressing my buttons. You really do have buttons. And so we exist in a moment where we're starting to learn how to really fundamentally press the buttons in ways that have never been available before, or that haven't been available for 80 years, but have never been given to the masses. So with that, I'd like to open it up to you. What do you think is important to look at here? How do we handle this going forward? The security community actually is the community to look at this. This is a cyber-physical systems issue, and I know cyber-physical systems are always the worst. They're complicated, they're weird. The real world is all around them. So now you're one. You have an implicit need to deal with this. And we would like you to talk to us. And I'm not just talking to you, I'm talking to you. Talk to us about where you think this needs to go, because we are studying this as we build it. And so in that sense, I think it's important that we involve this community. The Laboratory for Autonomy Brain Exchange is at labx@ucf.edu. If you'd like to reach out, not on Twitter, tweet us at Neurosecurity. And for right now, let me open it up to the room. What do you see that we don't? Thank you for your attention.
You mentioned ethics earlier on, but how can you actually test this on humans without actually, I mean, you could possibly see it happening in more repressive regimes, but how can you actually do this in the US? Do people have to volunteer?
I would never do this.
Undergraduates.
I mean, you can't, is the answer. Although I think it's going to get more complicated if you start seeing these things in the wild, right? So you can't create a true experiment. And you can look at a situation like concussions. Boy, concussions are having a moment, right? Traumatic brain injury is having a moment, both because of war and football, and other things. So here's a good example of how you do this. When you have enough in the wild, suddenly you have a sample, grimly enough. But I think you'll agree that there might be better ways to do this than to wait until there's a sample in the wild. On the other hand, this is the endless, difficult part of this type of research. There is no ethical way to study some things. And there's a long history of grappling with that. And so what we do is, in our laboratories, we look at the underpinnings in ways that are very ethical and work very hard to make sure that every undergrad is safe. and has no ill effects, and indeed is just building knowledge for everyone. The interesting thing is that the future is we believe, going to include things that we can't study, and I don't have a good answer.
So you showed the variable reward schedule video with the rat pressing the lever. So game designers have been doing this for a while. I mean, you could argue that Candy Crush and Angry Birds and those kinds of games are experiments in variable reward schedules to see.
And things going back much further.
Sure,
you know?
sure.
Human companionship is a variable
social media
reward schedule. Yeah, exactly.
Yeah. So that leads me to my question. How do we defend against, in the one case, I mean, do we wear tinfoil hats, or some sort of cloaking device, or something that'll cover our heads to protect us from Cuba-style sonic or whatever weaponry, and what can we do there, all the way through to how can we defend against viral ideas like white supremacy or something like that will cause people to snap and do things that that are not
we read
good
about too often.
Yeah.
I mean, I would have told you tinfoil hats were a bad idea a decade ago. But I do have
actually, just a quick, tinfoil actually amplifies the signals. So don't go with the tinfoil.
Yeah, it's true. It's true.
Yeah.
No tinfoil.
So what?
In terms of what to do about it, I think we have a large problem with that right now. I mean, it's all over. And the interesting question is, what do we do about technologies that people want but aren't good for them? And there's a long history of that question. Humans have had technologies that they want but aren't good for them since time immemorial. I do think, however, in this case, they've never come in such fast waves. So, we all have hesitations about Facebook. If you don't have hesitations about Facebook, you should. If we all have hesitations about social media and bubbles, they feel good, but are they good for us? Probably not. One of the interesting things that I think the research side can look at is understanding how people condition themselves. But I think the other thing is about speed. Conditioning yourself to Facebook or to your smartphone takes some time. Yeah. These rats condition in a matter of minutes. So that's, I think you'll agree, a pretty exciting difference. So the technology, which is neither good nor evil, is just extending our reach. And I think it's important to think about where our reach is now and where it's going. That's not a solution, but it is part of the dialogue that we want to have with the security community, and it's one you're already having. That's one of the wonderful things.
And I mean, the thing to understand about this is that rat, the rat's brain, that is the rat's brain's reward system that is being used, right? So when your child does something good and you get that positive feeling from that, that's exactly the same thing that's happening. It's just in one case it's happening from an electrical current, in the other case it's happening as a result of some action in the world. In terms of defending against it,
how do you,
yeah, that's why we want to have this conversation now.
Yeah, maybe by stopping it from happening in the first place.
Yeah. Right.
Science fiction from the 70s has already explored this point. The guy who did is named Larry Niven. His suggestion was that people who would indulge in these types of technologies generally died themselves of dehydration shortly after, and thus weeded themselves out of the genetic pool. I don't like that future, but Larry did. He thought it was funny.
All right, I'm sorry to cut this all off, but unfortunately we're out of time. Thank you so much for speaking. Thank you so much, everybody, for coming.
Thank you.
And if you'd like to come up and talk, we'll be here for a moment. Thank you so much.